Good morning, everyone. So, welcome to this teaching and learning seminar, and I'm making a start with my presentation, and it's going to be on deep clustering. My name is Marilyn, and I'm a PhD student here in uni, being supervised by Professor Leota, and my research is on real-time anomaly detection. So this is like one of the techniques that I'm looking at for my research. So today we're going to be refreshing on what clustering is, the techniques and the goals, and how deep learning actually improves clustering. Also some applications of this technique and the limitations of the state of the art and the open questions around it. So I'm sure most of us will be familiar with clustering. I don't know if any of us kind of work with it in our research, if we were doing anything where you're using some clustering techniques, but I'm sure we're familiar with the technique. So it's actually an unsupervised learning problem, used to solve unsupervised learning problem mostly, and its performance depends on the type of input data. You have like different similarity measures and different separation techniques, and it's kind of based on the type of data you have. So that's just a little background on it, and so we're going to, since we're familiar with clustering, we're going to just have an interaction to discuss why we think clustering is useful. So any ideas? It's going to be interactive most of the time. Do we have any ideas about clustering, why it's useful, or some applications of clustering? Any ideas?
To discover new knowledge?
Sorry?
To discover new knowledge?
To discover new knowledge, yeah. More like an exploratory analysis, yeah. Any other ideas?
To help us group together similar things.
Sorry?
To help us group together similar
yeah, so kind of in the exploration you tend to see some structure in your data, and then you're able to group some similar data together to do some further analysis of it. Yeah. Is there any other ideas about why clustering is useful?
To find communities. To find communities in a graph, for example.
To find
communities.
Common
Communities.
Communities.
In the graph.
A group of the nodes that has the same characteristic.
So similar interest, for example, from social media perspective. Finding people from similar interests.
Yes, similar, yeah, that's right. Yeah, so that's all right. So what I have here, some automatic data labeling in addition to finding similar. So you could use it to, for example, you have like an unlabeled data set, large data set, and then you just want to find do some automatic data labeling or some initial analysis for subsequent supervised learning of the data. You could use it then. It could also be like a pre-processing step for some data visualization and analysis. And also, which is what I'm interested in, is outlier detection. So you could, in finding those similarities, you could also find some bits of your data that it's not similar. You couldn't associate it with any groups, and then those are the points that could be classed as outliers. So for you to measure how good a cluster is, that cluster has to be representative. It should occur frequently enough in the visual world. For example, have like the red dots here that are much more predominant than the other points, and then it should be discriminative. That is, it should be different enough from the other points that are in that world. And then you could find you could use like some distance measure, like to find out the similarity and all of those in the cluster. So supposing you have a cluster, let's say you have a data point, and then it's been clustered into like two major classes, and then you have like a classifier H that clearly separates the data set into two clusters. So here you find that this H acts like a linear classifier, because clearly your data has like two very separable points. So you have H, they're acting as a classifier. And one thing we need to realize about clustering is that it almost preserves the underlying structure of your data and the distribution. So that's to say that if you have your data points, for example, your cluster is actually to find like some structure, some grouping or similarity with data. What it doesn't do is to try to maybe compress it or to do some merging. So your clustering, what it does is to have like find some in the distribution of the data, find some similarity, but it doesn't do any sort of compression. So it's like what the data you feed into it is what it uses to find the structure. So now a question: can we build a linear classifier for this sort of data distribution? Yes or no?
No.
You're going to give me your reason? No. Okay. So why? Why no?
Because probably the data is like in different locations. It can't be run a linear line for it to sort of separate. Okay, this is this point red or this is point blue.
Yeah. So okay. So it's saying that the data is. I mean, as you can see, there is no linear separation in the data set. So you can do any yes. Can we? We all agree with no. Well, what if I say yes? Yeah, so if you're able to kind of project your data from the input space to a feature space, into a higher dimension, you could be able to, find a classifier that could separate that data. And that's what happens like in the feature space, and you use some canal function, more like a canal trick to be able to do this mapping in feature space to perform that separation. And that is what your deep learning actually helps to do, to transform the data from the input space, where it's difficult to separate, into some feature space where separation gets easier. So let's look at clustering with deep learning. So you have your input image, and then it goes into an encoder. And it goes into the latent space where some dimensionality reduction and representation learning happens. And through that, you could then have your clustering, happening, and you can update the network and improve the clustering objective. So your data is basically going from the data space to the feature space, and where you can improve on the clustering through this technique. So that's the idea of using deep learning. So deep learning is actually helping to improve your clustering by helping the separation of your data in the feature space. So we're going to be doing a little exercise. So I have this. We're going to be mapping the techniques we have here into one of these diagrams. So we're going to be doing some matching. So you're going to tell me, for number one, which of the diagrams here would fit into it and so forth. Okay, so raw data space, A, B, C, or D.
We are acting right now as undergraduate students.
Sorry?
We are acting right now as undergraduate students. You don't want to make eye contact.
I'm not at all sure, but I would plan for C.
Yeah, I will agree as well. You just
Okay.
need to warning and nothing.
Yeah, that's correct. C, because when your raw data space, you just have like data, the other points.
There's no other
there's
distinction between.
Yeah. So then, what about k-means clustering? Which of the diagrams look like it? It's just to give us an intuition into it, really.
I think A because A has this star as a beginning.
Yeah, A. Yeah, that's correct. And then the discriminative clustering, or like when when you're using like a linear SVM classifier to help in the separation.
D maybe?
Yeah, D. Yeah, because you know your SVM, you have like the support vector, and then you have the hyper-optimal, although it's not here, but normally you have like an optimal hyperplane and then the support vector here. And then of course, clustering with deep learning. So what the intuition is just that the deep learning is actually helping to improve how discriminative the points are, helping to kind of make them much more, grouped together. Yeah, that's just the idea. So as much as possible, what we want to do is to improve the discriminative nature of your cluster. So that's what, so by applying the deep learning and then optimizing your clustering objective, you're going to have your cluster much more discriminative as you keep iterating through the data set. So we're going to look at typical application of this technique. So you have a group of images, so you'll be able to separate them into, you could find that when you apply this technique, you could find your clusters with images that are similar, in some form. Like for example, you have the birds and the frog clustered around this point, and then you could find that there are some large size images and small size images in your cluster, or based on the shape, you could find similar shape, because with your, let's say if you're using a convolutional neural network, you know that there's some kind of hierarchical learning that goes on, so there's, so it's kind of separating the features, using some filters to, group your image into some form of cluster based on the feature. It could be that these ones are circular in shape, these ones are straight lines and all that sort. And if you have like, you could run a query and then you'll be able to return images that have similar features that look similar in your data set. So for me, I'm actually looking at applying this technique in real-time anomaly detection. And so this is the state of the art. You have a set of images, or in this case video, of course, like processed into frames, continuous frames, and then pass them through the spatial temporal autoencoder. And this is actually basically CNN and long short-term memory, And during the training, it's able to kind of learn what's normal. And at the testing, you then introduce the normal and the anomalous, and then based on the RMSE, there's a mean square error. You find out that for the anomalous, you have like a higher mean square error because it's different from the other images that the network has been trained on. So it's going to have like a higher score for the anomalous images. Yes. So, but the limitation in this is that it's for real world application. For example, let's say we deploy a camera in this room, and then we have it running, let's say, at training time, and then at some point you switch detection mode or something. So at training time, of course, we expect that the normal activities that happen here, maybe people sitting down, standing, walking, it's going to be like much more frequent. And then anomalous, say people running, it's going to be, like a very rare occurrence. Yeah. So in real world scenario, training is actually going to, you need to do your training online, at least in mini batches. And then you're not just going to train on normal data set like what they've done here. So they'll just like train on the normal, and then at test you just have like introduce the anomalous, right? And also you're willing to have like you're not going to just have a single activity happening in the scene. So let's say people walking, standing, and sitting. These are three different kind of activities that could be happening regularly in this scene. So it's not just going to be one activity. So that's so the question now is, how do we characterize activities in a truly unsupervised fashion? Yes, they said, okay, this is unsupervised. Probably yes, they've used a convolutional neural network or special temporal autoencoder for the training and the testing. But yet, we have like these limitations that make it impracticable for real-world scenarios. So how are we going to characterize activities in a truly unsupervised fashion? That's the question I'm trying to answer. And the intuition behind using deep clustering technique for anomaly detection. So you have, you're able to, your model is able to learn, by grouping those activities, so the data it receives into different clusters. You're not interested in classifying to say, oh, this is working, but based on what your model learns in an unsupervised way, you could find some similarity, in the data set. And then when you have the outliers, they are going to be way different from the other activities, the other points in your data. So, and then this is what the deep learning could help to do, to improve the discrimination. Remember, by kind of projecting it from the input space to the feature space, you're improving the discrimination and the ability to separate. And then you find that the less representative data points become possible anomalies. So, so I was looking at some work that's been done. This one is just on image data. I don't know if you're familiar with this MNEST data set. It's like handwritten digits, 0 to 9. And then they've used this deep clustering technique to perform, to run this data set. And you can find, if you look at this is like to visualize, I don't know if it's visible to you. So this is like zeros, then twos, and then ones, sevens, 9, 8. So you can find that there's some in the feature space. There's already some, clustering that's happened here, like some distinguishing of the data. And so if you do perform clustering on it, you're going to have, this represents digits 0 to 9. So you're going to find those digits, those clusters representing those digits. But now there's some limitation, because already we know that in this MNEST data set we have 0 to 9 digits, right? And then we already know that it's going to form, 10 clusters because we have those digits. So we have like some predefined heuristics of the data, and we know that. So we just impute n equal to 10, and we're able to obtain this. Well, so it means that we need a prior knowledge of the data set structure. But what if in this situation, like in this real world scenario where we have like a camera looking at this thing, we don't want to really predefine the number of activities, right, that could happen in the scene, right? Because we are looking at the unsupervised learning. We just want some, knowledge, some self-learning that to go on. So this is a big limitation for the sort of application we're looking at. And the question is now, how do we limit the parameterization for real-world applicability of this?